In this, episode 4 of Working with R²S, we're going to add in volume control to our circuit and software. Roll the titles.
Is that it?
As always, time codes and affiliate links for the kit shown are in the video description. It is recommended you watch the previous episodes in this series. Links are also in the description. How do we reduce the volume? Remember, this is digital data. So if we reduce the size of the numbers, we will reduce the volume. Simply multiply the numbers by, say, 0.5 would halve the volume. Times by 1 and it will remain the same. Times by 1.5 and it will go louder, etc, etc. In code, we now know we'll just use a decimal number somewhere probably in the range 0 to 2 would give a volume range between 0, silence, and twice as loud. We just need a way for us to change this number. All we need is some sort of input for our ESP32 to use to set the volume. So let's look at our options. You could have two buttons, a volume up and a volume down, looking at which is pressed in code in order to then manipulate the volume variable. Or you could have a dial that you turn that sets the volume. I'm going to show the dial version. Here it is, a simple potentiometer. The value of this one is 10k, but you could use 100k or 1 meg. It makes no difference to how this will work. The only thing I would say would don't go lower than 10k, as the lower you go, the more current will be used needlessly. The reason it doesn't matter what the value is, apart from the caveat I've just mentioned, is because we are going to wire this as a potential divider. As you can see, there are 3 connections. We wire one side to ground, one side to VCC, then the middle will actually put out a voltage that is proportional to the position of the dial. Cool, eh? Well, it is for people like us anyway, isn't it? We can measure voltages on virtually all microcontrollers, and the ESP32 is no exception. In fact, it has many analog to digital converters, or ADCs, available, and we can use most pins to access them. In my example, just for convenience of my breadboard layout, I'm going to use pin 14. We've got 3 wires already in the circuit, one to ground, one to VCC, and one going to pin 14. They are positioned just so I can slot in this potentiometer and the connections will be correct. As you can see, one side going to ground, one to VCC, and that middle one going off to pin 14. The updated circuit diagram is on screen now. Pause if you want, or if you want, pop along to my website where you'll find the diagram and the full demo code. Link, as always, in the description. Let's look at the code. This is only a few extra lines, and it's all done in the routine that reads from the SD card. So after we've read in that 1k's worth of data, we go through all those samples and adjust each one for our volume setting. First job, get the value from that potentiometer with this line here. The analog read, as default, will return a value between 0 and 4095, representing the voltage measured from the potentiometer. So 4095 will be around about 3.3 volts. We need it in a suitable range to apply to our sound samples though. As mentioned, a value of 0.5 would halve the volume and 2 would double it. So a bit of maths required here. I've divided by 4095 so that the max value for volume would be 1, i.e. max from analog read is 4095. Divided by 4095 would be 1. As analog read can't return a value bigger than 4095, our maximum value will be 1. And this will give us a range of between 0, silence, and 1, full volume for this particular sample. If you wanted to make the sample even louder than originally recorded at, then you could lower this number. For example, halving it would give you a range between 0 and 2, 0 and twice the volume. You may wonder what this float thing is about. Well, as a certain popular electronics blogger from Aussie would say, here's a trap for young players. I won't try and do the accent, that'd be embarrassing. The value returned from analog read is an integer. And if we don't have this, then the compiler looks at this and basically presumes we want integer division and returns an integer value from this division. So whole numbers. Which would mean if we only have a range of between 0 and 1, then all that it will return will be either a 0 or a 1. Either no volume or full. No in between. Not exactly what we wanted. So what this does is a thing called typecasting. It converts one type of variable to another. So in this case, we get the integer result back from analog read, and we convert it from the type integer to type float, i.e. with decimals. The compiler then does a floating point division and returns a floating point decimal answer, which is what we want. For young players, this can be a real doozy of an error to spot or know what's going on. Some computer languages are better at handling this than others and will intuitively know you want a float. But that can come with its own problems as well. More years ago than I care to remember, I used to code in a language called Ada, named after the rather remarkable Ada Lovelace, largely regarded as the world's first computer programmer in a time when only gears and mechanics existed. Not even valves, nothing. They were twinkling somebody's grandson's eye. I'll put a link in the description to a video about her. Really worth a watch. She was an amazing person. Ada, the language, is a heavily typed language, and you could not have made the error we see here in our code, as the compiler would not let you do maths on two different types of variables. It would generate an error. So you would immediately know there was a problem. You're not even going to get a final compilation. You would have to explicitly typecast variables to get the result you want. This may sound fiddly and annoying at first, but it leads to code that is much more robust and less error prone out in the field, and is used in many mission critical situations where you want a reliable solution. Moving on, waffled a bit there. In this loop, we go around all 1024 bytes of data. Remember though, that each sample for left and right channels is a 16-bit word, 2 bytes. So we go around the loop 2 at a time. These lines may look complicated with all the brackets and the asterisks, but all they are essentially doing is multiplying a sample value by our volume setting. The complexity comes in because we have our samples stored as 2-byte integers in one long continuous buffer. It's getting those values out of there and putting them back in afterwards that makes this code look complex. Let's break it down line by line. We need to get our sample and put it into the variable called signed integer. This line does that. Samples is the address file buffer of samples. The loop variable I is the current offset into that buffer. So in the first instance, it will be 0, and so we are looking at the start of our samples buffer. Next time round, the loop I will be 2, so we'll be looking at the start of the next sample in the buffer, the next 2 bytes, which is our 16-bit word. So within these brackets, we get the address we want to get our value from. Now, samples is defined as a pointer to an address containing bytes, which of course it is. But within these bytes, we actually have 16-bit integers. So this part tells the compiler to treat this address as the address of a 16-bit integer. So now within these brackets, we have a pointer, the address of a 16-bit integer. This asterisk then basically says, give me the contents of that address. It is not being used as a multiplication symbol in this instance. Maybe The C Language Design Committee should have used a different symbol for this than the asterisk. But hey ho, it's what it is. Other computer languages did it differently, and it made code easier to read, but anyway. So we now have the contents of this address as a 16-bit integer, and we store it in the signed sample variable. Next line is simples. We multiply it by our voltage value and store it back in the signed sample variable. We now have to get this new value back in the location it came from. So some more jiggery pokery with pointers and stuff. You can see that this is identical to this part, as it's doing the same. It's saying make the content of this 16-bit integer address equal to the value stored in signed sample. And we're done. The R loop counter increments by 2, and we move on to the next sample and do the whole thing over again, but for that particular sample. Now all those 3 lines of code could have been put into one single line, and here it is. And some coders would argue to do it that way. You take your choice. To understand and explain what's going on, it's easier to use the 3 lines. Even for a lot of coders, they would have to stop and think about what's going on here. Personally, I think that code should be easy to read, but I've met some characters over the years that would write code in very, very clever ways, but it would be hard to follow for lesser coders such as myself. And making code easy to follow is what's required, in my opinion. So let's make one quick alter to this code and make it so we can have a volume range from 0 to twice as loud. And then I can show you what happens on some samples if you play a sound too loud. So we'll put a value of 2047 in here, and that will do that. Let's upload and look at this in action. Volume is set about halfway. Let's plug in. Moving lower. Moving back up. All good. Now listen what happens if we keep on increasing. Just turn that back down. We have distortion and corruption. What's happening is we only have maximum value for 16-bit integers, which is 32,767 positive and minus 32,768 negative. If we multiply our volume and get a value bigger than this, then we will get this distortion. We can't physically store a number higher than what this 16-bit integer will store. However, if the audio we are using is very quiet, then this would be fine. Most audio samples, particularly songs that I've come across anyway, are approximately set at the same volume of around 75% of the max-ish. I'm no audio engineer. But having a range that can go twice as loud is handy for quieter audio. So that's the level I'm going to leave mine at. That wraps up this episode. Next time I'm looking at mixing more than one sound together, i.e. playing more than one sound at the same time. At least I think that's my plan. It could change. I'm not going to promise. Till then, thank you to my patrons very much. To those that hit a like on the video, to those that have just subscribed, and to those that are already subbed, thank you. Whether you fit into any of those groups or not, thank you very much for watching. Till next time.